Welcome to This Explainer. Look, if you've ever stared at a mountain of database concepts and felt your eyes just glaze over, yeah, you're definitely in the right place. Today, we have something incredibly special. We're exploring a comprehensive, authentic set of handwritten study notes. Think of these notes as the ultimate cheat code to conquering database architecture and interviews, without falling asleep in a textbook. We're going to decode the ink and translate it into pure, actionable understanding.
Here is our survival roadmap. 1. The blueprint, ER models. 2. Keys to the kingdom. 3. Normalization, cleaning up data. 4. Speaking database, SQL commands. And 5. Playing it safe, transactions.
Okay, let's dive right into Section 1, the blueprint, ER models.
So, the foundation of this whole phase is the entity relationship, or ER model. I know, it sounds super intimidating, but honestly, it's really just a diagram. Imagine we're building a university system, right? A student is an object. We call that an entity. The things that describe that student, like their name or age, those are attributes. And how that student connects to a course entity, well, that's the relationship. It's basically the architectural blueprint of our database.
And if you look at how these authentic handwritten notes visually ground these abstract concepts, it's pretty amazing. On the left, we've got the breakdown of attribute types, single, multi-valued composites, and on the right, the mapping of functional dependencies. What I absolutely love here are those little callouts for the GATE exam at the top. These notes aren't just dry theory, they're literal cheat codes highlighting exactly what you need to know to pass those high-stakes technical interviews.
All right, moving on to Section 2, Keys to the Kingdom. Now we're talking about the foundational bedrock of relational databases. And by the way, a totally classic interview question. Side by side, we have the primary key and the foreign key. Your primary key is the absolute unique identifier for a row. Think of it like your social security number or a unique student ID. It cannot be duplicated, and it definitely cannot be blank or null. The foreign key, on the other hand, is the bridge. It references the primary key of another table to link them together, which maintains what we call referential integrity.
Now, what's really interesting here is that massive IMP tag right in the middle of the notes. It stands for important, and it points directly to rules about foreign key integrity. You see, if you delete or update a referenced data point, let's say a specific course that a bunch of students are enrolled in, you have to tell the database what to do about it. Do you restrict the deletion? Do you cascade it and delete the student records too? If you don't handle this properly, you're going to cause massive system violations.
So let's clean things up in Section 3, normalization, cleaning up data.
Think of early data storage like a disastrously messy closet. Normalization is essentially a series of escalating levels of Marie Kondo-style cleaning for your data. First normal form, or 1NF, gets rid of multi-valued attributes, so, no cramming 3 phone numbers into one single box. 2NF removes partial dependencies. Then 3NF gets rid of transitive dependencies, which is just a fancy way of saying a non-key attribute secretly relies on another non-key attribute. And finally, we reach BCNF. This is the strictest form, demanding that every determinant absolutely must be a superkey.
These concentric circles brilliantly illustrate BCNF as the inner bullseye of data perfection. By the time you shrink your tables down to BCNF, you are ensuring what the notes call lossless decomposition. Basically meaning you've broken your tables apart to remove all that annoying redundancy, but you haven't lost a single drop of actual information.
Let's look at the real villain of data redundancy straight from the notes. Notice how Store 1 is always in Delhi and Store 3 is always in Mumbai. Now, imagine if we add 1 million customers to Store 1. We'd have to type Delhi 1 million times. That's a huge waste of space and honestly a total nightmare if the store ever moves. By applying normal form rules, we split this table up so the store-to-location relationship is stored exactly once.
Okay, Section 4, Speaking Database, SQL commands.
SQL, or Structured Query Language, well, it's really just a highly specific, slightly demanding way of asking the database to do your chores. You don't have to write complex procedural loops to find something. You simply declare what you want, like select the maximum salary, and the database engine just figures out how to fetch it for you.
To keep things organized, the notes break SQL commands down into distinct families, kind of like different tools in a tool belt. DDL commands, like create or drop, they're the heavy machinery. They build or destroy the actual tables and structures. DML commands, like insert or update, are your precision tools. They manipulate the rows of data inside those structures. And TCL commands like commit and rollback. Those are basically your save buttons and undo buttons.
And this brilliantly illustrates the handwritten breakdown comparing alter and update. This addresses a very common point of confusion for beginners. Because, they sound super similar in plain English, people mix them up all the time. But the notes make it explicitly clear. Alter is a DDL command that changes the structure of a table, like adding a whole new column. Update is a DML command that changes only the data inside an existing row.
Here is a raw employee salary table directly from the notes. This is the exact kind of data you use SQL to interrogate. Using aggregate functions, you can ask for the max salary or group the data to find the average salary per department. The notes even show how to use nested subqueries on this exact table to find the second highest salary. Oh, and a quick pro tip from the notes. To make complex searches like this run at lightning speed instead of painfully scanning row by row, databases use indexing. It acts just like a roadmap for your queries.
All right, which brings us to the final stretch. Section 5, playing it safe, transactions. Imagine this terrifying scenario for a second. You're transferring $500 to a friend. The database deducts the money from your account, but exactly 1 second later, before adding it to your friend's account, the power goes out, the server crashes. Did your money just vanish into the digital void? Well, without transaction management, yeah, it did. But thankfully, the DBMS acts as a superhero to prevent exactly this. The framework that prevents our money from vanishing is outlined in the notes as the ACID properties. Think of ACID as an overly strict bank teller. Atomicity guarantees that a transaction is an all-or-nothing deal. Either the whole transfer happens or none of it does. Consistency ensures no database rules are broken during the process. Isolation ensures that if two people transfer money at the exact same millisecond, they don't corrupt each other's data. And durability means that once the database says transfer complete, that change is permanently saved, even if someone literally pulls the plug from the wall.
Let's actually trace the journey of a transaction using this handwritten state machine diagram. A transaction starts as active in the computer's memory. From there, it goes to partially committed. Now, if everything is absolutely perfect, it moves safely to committed, and the data is locked in on the hard disk. But if a failure occurs at literally any point, it falls into the doomed failed state.
So the crucial point is this exact quote captured in the notes. A failed transaction can't be resumed, it will roll back. Databases are incredibly unforgiving, but in the best way possible. If your $500 transfer hits a snag halfway through, the system doesn't try to stitch it back together later. It immediately rolls back every single step as if you never even clicked transfer, saving your money from being lost in limbo.
But even with safeguards, concurrency, meaning many things happening at once, causes some major headaches. Look at the dirty read conflict diagram sketched out here. This happens when transaction 1 updates a value, but before it can formally commit, transaction 2 sneaks a peek at that uncommitted data. If transaction 1 subsequently fails and rolls back, transaction 2 is now working with dirty, imaginary data that technically never existed. It perfectly illustrates why that isolation property we just talked about is so absolutely vital.
So, what does this all mean? We've covered the entire journey, from sketching the raw ER blueprints and defining our keys, to aggressively normalizing our tables, writing SQL queries, and protecting the whole shebang with ACID properties and indexing. These handwritten notes are a literal masterclass in breaking down database theory into practical survival skills. So I'll leave you with this thought. If your own personal life's data was a database, which normalization form are you currently stuck in? Are you crammed full of redundant, messy data, or are you operating in pristine BCNF? Think about what tables you need to clean up today. Thanks for joining me on this explainer, and keep learning.